Hello everyone. We're going to be looking at the properties of logarithms today. So some main things to take into consideration while working with this is how to simplify logarithms and how to convert logarithms into exponential form, as well as going from exponential form into logarithms. So logarithms are the inverse of exponentials, and so we're going to be looking at logarithms in terms of exponentials a lot while we're working with this. So remember, with exponentials you have the base b, which for an exponential that number is going to be constant, and then you have your variable, your independent variable, which is going to be your exponent x. Excuse me, and notice that its location is in the superscript position. Okay, so the variable is always an exponential function going to be in the exponent position. So when comparing that to the logarithmic function, the base is written as a subscript this time, so that tells you what you're looking for, and the independent variable is written in the in line with the logarithm. So the notation is going to look a little bit different from what we're used to, but it's okay. So we have a couple of major properties that we're going to be looking at, the first of which is the product property of logarithms. And so what it states is that if you have a logarithm that is logarithm base b, that is the product of two numbers, that is the same as the logarithm of the same base of one of the factors plus the logarithm of the same base of the other factor. So in the example here, log base 2 of 8 plus log base 2 of 4, well, we can look at this property, here in reverse and see that it's going to be the product of these two factors, 8 and 4. So we condense this into a single logarithm, log base 2, so the bases have stayed the same the entire time. And then this is going to be 8 times 4, which is 32, and then log base 2 of 32 is going to be 5, because 2 to the 5th power is 32. So we have three examples here. The key things to pay attention to is that in every case, A, B, and C, the bases are the same. Log base 6 for A, log base 5 for B, and log base 1/3 for C. And then it's just, you take the two values of the independent logarithm, so an A, 4, and 9, and you're going to multiply those together. In the case of B, the 625 and the 25, and in C, the 27 and 1/9. Once you find those products, then you can take the logarithm of the single number. So log base 6 of 36 was going to be 2, because 6 squared is 36, and so on for the other three. The quotient property, it shares its similarities in that if you have a logarithm that is the ratio of two numbers, that you can take the numerator of that logarithm and subtract the denominator of the logarithm. So we have here in our example log base 3 of 54 minus log base 3 of 2. So we're going to reverse this property. I have the subtraction of two logs, same base. So then that gives me 54 divided by 2, which are where the two different independent values. And 54 divided by 2 is 27. Log base 3 of 27 is going to be 3, because 3 cubed is 27. Again, just like in the products, notice that the bases in these are always the same. So for A, it's base 5, B, base 7, and for C, base 3. You take the two independent values, 100 and 4. Since this is minus, we're going to divide in the logarithm to give us 25, and which log base 5 of 25 is going to be 2, and then so on for the other values as well. Okay. Inverses just state that a logarithm with a particular base of a number of the same base results in just the exponent being the answers. And so this is the case for A, B, and D. You can see that for A, this is log base 3 of 3 to the power of 11. And when you can go through and you can do the math, you could expand 3 to the 11th power and then take its logarithm and see that eventually it just takes you right back to where the exponent 11 just ends up being your answer. We can advance this a little bit more. Log base 3 of 81. Well, 81 is 3 to the 4th, and so log base 3 of 3 to the 4th is just going to be 4. In logarithms, if the subscript, if the base is not listed and it's written as log, that is understood to be base 10. So this line right here is actually saying log base 10 of 10 to the power of 0.9. So your answer is going to be 0.9. We can reverse this process and look at it in terms of an exponential. An exponent of a particular base, so in this case this is 5 to the power of log base 5, the independent value of the logarithm is just going to end up being your answer. So 5 to the power of log base 5 of 10 is just 10, and then the same is true here. So as for problem E, you can, if you take a look at this, this is 2 log base 2 of 8 to the power of x, and so since the exponent and the logarithm are the same base, then the answer is just going to be the independent value of the logarithm, which was just 8x. So getting more specific into what a logarithm is, I mentioned at the beginning that the logarithm is the inverse of the exponential, and so we can actually write each value in terms of the other. So if you're given an exponential, you can write it as a logarithm, or if you're given a logarithm, you can actually write it as an exponential. Key things to note: the base always stays the same. So b to the power of x is going to equal some number a. Well, then the logarithm of base b, so b is the same value, of a is equal to x. And so the way that I interpret logarithms is I say, okay, b to what power is equal to a, and that power value is what is going to actually be x. So when we're converting between these, so I'm going to kind of switch back and forth as we're reading some of these. 3 to the power of 5 is equal to 243. Well, if I were to write this in terms of the logarithm, then that's log base 3, so I'm keeping the same base. Log base 3 of 243 is equal to 5 because 3 to the 5th is equal to 243. So for the next line, log base 25 of 5 is equal to 1/2 because 25 to the power of 1/2 is equal to 5. 10 to the power of 4 is equal to 10,000. That's a 1 with 4 zeros behind it. Is equal to log base 10 of 10,000 equaling 4. They are equivalent. They are equivalent relations. Now, one of the things with this log base 10 of 10,000 equaling 4 is that you can write it as log 10,000, because if you do not see the subscript and it's written as log, it's assumed to be base 10. So that's a pre-programmed function into your calculator. And as we move through with the rest of these, you can see that the pattern is the exact same. 6 to the power of -1 is 1/6. So log base 6 of 1/6 is -1. A to the power of b is c. Log base a of c equals b. Okay. Now, earlier we looked at condensing logarithms, but we can also expand the logarithms, and they sometimes each one has its advantage, and sometimes it's easier to condense, sometimes it's easier to expand, and that just depends on the problem. So when you expand the logarithms, we're taking that same property. So this is case log base 2 of 40 divided by 5. Well, so you go with the numerator first, keep your base the same. So this will be log base 2 of 40, log base 2 of 40. Because it was division, then it's going to be minus the log of the denominator, so log base 2 of 5. In the case of B, this is multiplication, all base 4. So log base 4 of x. So this is x times y cubed. So since there's an understood multiplication between the x and the y, we get plus log base 4 of y cubed. Log base 3 of x divided by 4. So this is your quotient property. So there's going to be a minus sign. Numerator goes first, denominator goes second, and the bases stay the same. Log of 5a, so this is an understood log base 10. This is a product, 5 times a, so this is log 5 plus log a. The power properties of logarithms. So if you have a logarithm of a base of a number raised to a power, then you can take that power and just move it out front. You can move it out front into the to turn it into a product of the logarithm. So in this case, example A, this was log, again, this is base 10, but log 10 cubed. If I take this cube, if I take the 3, I can move it out in front and multiply it by the logarithm. So log of 10 to the third is the same as 3 times log of 10. Log base 4 of 50 to the power of 2x. You take this 2x, move it out front, so this is 2x times the log base 4 of 50. We've already kind of looked at this, but now we're just kind of formalizing it a little bit better. Inverse properties of logarithms and exponents. This is log base b of b raised to some power. It's just going to result in that power. Or the exponential b raised to the power of log base, the same base b of x. It's just going to be that independent value. So log base 5 of 5 to the power of -1 is -1. 4 to the power of log base 4 of 10 is just going to be 10, and you can see that the pattern is going to continue with C and D. All right, so reviewing the properties of exponentials, if you're looking at the function of 2 to the power of x, you'll see that the domain is all real numbers, and that the range, it starts at 0, but not including 0. So you're gonna get infinitely closer to the x-axis when you move off to negative infinity, and then it's going to start to turn upwards and continue to increase more sharply upwards. Another way that we describe when we're talking about the functions is we say it has an asymptote or isomotope along the x-axis in the negative x direction. So the logarithm, in comparison, if you draw the line y equals x on the graph, has been mirrored exactly over this line of the exponential. So log base 2 of the x, notice that the domain and the range of the exponential have switched places. And so whereas the range, you start at 0 exclusive, and move towards positive infinity, or we say just as long as your range is greater than 0, then in your logarithm, your domain, your x values are also greater than 0. In the exponential, where your domain is all real numbers, that is your range in your logarithm. I've already mentioned the logarithm. And log base 10, that is log. When it's log and there is not a subscript, that is understood to be log base 10, which has a name. It's called a common logarithm. And but there's another one, and that is ln, which is the natural logarithm. That is log base e, the natural number e, which is approximately 2.71828. Okay. Other properties of logarithms. So we dance around these when we were talking about the inverse logarithms. Log base b of b, it's just going to be 1. So any base number of the same number is always going to be 1. And again, think about this in terms of exponentials. This is saying 10 to watt power is 10. That's 10 to the first. 4 to watt power is 4. That's 4 to the first. And x to watt power is x. That's x to the first. And there's another common property, log base b of 1. That's going to be 0 for any valid base. Because if you look at number 4, log base 10 of 1, that's 0 because 10 to watt power gives us a value of 1. It's going to be 0. 25 to the power of 0 gives us 1. And 2 to the power of x, 2x to the power of 0 is going to give us 1. Here's just a couple of quick exponentials, a couple of quick logarithms, that you can look at and evaluate mentally. And then when we start talking about graphing functions, I use Desmos in a lot of these, but the overall idea that whether you use Desmos, whether you use the graphing calculator, whether you use the function, whether you use the data table, the same system is always going to be at play. If you're given a function, and then you are given selected values x, then you need to take each value, you need to plug it into the function. 1/3 to the power of -3 is going to give us 27. This function to the power of -2 gives us 9, -1 gives us 3, and so on. And so then you get this data table, and then from this you can either by accessing the table and the calculator, if you graph the function, or by plotting the points, you can eventually generate the graph. When finding its inverse, remember we keep the base the same. And it's we're going to keep the base the same. I'm marking the independent value as x. In this case, notice that when you plug in any of the numbers that are exactly 0 or less, we're getting an error. That's because it was not defined within the domain. You have to be greater than 0 for the logarithm. But when you're but for any value that you can think of in the range, there does exist some value x that's going to give you that number. Okay. So In the next section, we're going to be looking at how we can solve exponential equations using logarithms.